For our second speaker this morning, I'm very pleased to introduce Lorenzo Foscolo, who's going to tell us about hypertoric varieties, W-Hilbert schemes, and Coulomb branches.
Thank you very much, Jason, and thanks very much to the organizers for the invitation to be here and speak here. So this is what I'm going to talk about is joint work with Roger Bielaski. Apologies to people who have listened to these already. So anyway, so the sort of motivation for this was realizing that certain constructions, in particular sort of Twistor constructions of decay ALF matrix, actually seems to generalize to higher dimensions, to sort of classes of non-compact hyperkähler spaces, high-dimensional hyperkähler spaces that have geometry that generalizes the geometry of ALF spaces. I mean, probably the results in the end are definitely much less conclusive than we would have hoped for. But I mean, this is what I'll talk about. So let me start with sort of the real four-dimensional story where, first of all, let's start with the Gibbons-Hawking construction that Claude told us about the other day. So here, so this is about hyperkähler for manifold with this ALF asymptotically locally flat. Asymptotic geometry. So in this talk, what is going, because in the end, we're going to emphasize sort of Twistor methods than what's going to matter more is sort of the generic complex structure on these compatible with the hyperkähler matrix. So for the Gibbons-Hawking matrix, then in a generic complex structure, we have the sort of a kind of deformation of the AK-1 singularity. So this is just a equation. It has a hypersurface in C3. Lambda i's are just a k-distinct point in C, and sort of these kind of deprojection onto the complex Z-plane sort of exhibits these complex surfaces as fibrations where the generic fibers are copies of C star, and then over the points lambda i's, then we have kind of nodal C stars, so two copies of C that meet at a point transversely. And well, as Claude explained in the Gibbons-Hawking ansatz, we kind of hyperkähler upgrade this picture where now the parameters, instead of just being complex parameters, they're distinct points in R3. We go from a C star fibration to a circle fibration over R3 with K points removed, and which is a principal circle bundle. And then to write down the metric, we also need a positive parameter L, and sort of the so this is just a constant L, and sort of the metric, so this Gibbons-Hawking metric or multi-tau nut metric for L positive constant is going to be sort of ALF, which again very roughly means that we have this asymptotic geometry where we have at infinity a Riemannian submersion where the bases are flat R3 and the fibers are circles of radius L. And then we have these we can actually push this constant, formally this constant L to infinity in a way, in the sense that we're going to have as a limit of these family of ALF metric, ALE metric, so maximum volume growth metric, where somehow this circle fibers at infinity have become infinite length as well, and we get an ALE metric asymptotic to C2 mod ZK. Okay, so
it might be helpful for people that are connecting the two pictures to know that. So where's the other parameter? It's the size of the exceptional divisors, right? So each one, the Kähler class.
Right. So for generic, so complex structures in the Gibbons-Hawking ansatz, complex structures corresponds to choosing directions in the base R3 of the Hypertoric moment map. So here, this lambda I, this point in R3, can be thought as point in C plus sort of a real kind of parameter, and then if we choose the complex structure corresponding to this splitting, if the lambda I, the complex parameters are all distinct, then the complex structure of that surface is precisely, the complex structure of that surface is precisely this sort of affine variety, and instead where some of the complex lambda I come together, then the freedom that you have to consider now distinct real parameters corresponds to doing minimum resolutions of that. Sort of this affine variety would be singular, and then the real parameter encodes sort of the choice of a kind of Kähler class on the minimum resolution of that singular complex affine variety. Yeah, thanks a lot. Okay, so so if we go to the dk, surfaces, then again we can start from the complex case. We have a dk singularity, and their sort of versal deformation space. So again, these are given by their hypersurfaces in C3, given by some explicit equations depending on parameters. Again, lambda 1, lambda k. So this is the equation of the generic dk surface, and sort of is going to be relevant later, a special subfamily of these, where basically if you set one of these parameters to 0, you still get a smooth, but all the others are distinct, then you still get a smooth surface with sort of this simpler equation and a Z2 action that corresponds to changing x and y into minus x minus y. Okay, so this is from the complex point of view, and then actually getting Hypertoric metrics on these spaces is much more involved, in the sense that they're not going to have, in general, continuous symmetries that allow us to use the magic of the Gibbons-Hawking ansatz. So one way of thinking about this metric was sort of suggested in the physics literature by San, and then done, sort of carried out rigorously more recently by Schurz and Singer. So very roughly, sort of one starts with the sort of the simplest dk surface, the D0 case. So we have this D0 surface. This actually carries explicit Hypertoric metric, the Atiyah-Hitchin metric. So in this case, actually, there are continuous symmetries, and actually is a homogeneity one Hypertoric matrix that can be given in terms of solving some ODEs. And sort of the asymptotic geometry of this looks like a Z2 quotient of Taub-Knot metric. I mean, of a sort of, we have these ALF asymptotics, except that we need to quotient by a certain Z2 action that on the circle fibers in particular sort of reverses the orientation of the circle fibers. And then also, if you look at the topology of this circle bundle at infinity, that we have a sort of this negative charge for this circle bundle at infinity. So that's what it is. This is a metric that we know that exists. So this D0 surface is actually not simply connected. So get for free another Hyperkähler metric by looking at the double cover. This is going to be sort of this special D1 surface. So again, the asymptotic geometry is as before, so a Z2 quotient of a Gibbons-Hawking metric, and now the sort of charge at infinity, though, since we come to the double cover as sort of a half of the original one, so -2. Okay, so these are known, and then Sen's idea was to imagine something like this, where sort of you start with a Gibbons-Hawking metric starting with 2K points distributed in a Z invariant fashion. And you also put some negative charge at the origin. This could be charge -4 or -2, quotient by Z2, and then sort of you can imagine, because you've chosen this charge and quotiented by Z2, so that now near the origin, things look like the sort of infinity of this Atiyah-Hitchin metric. So you can imagine sticking this in, and sort of to see a very small copy of Atiyah-Hitchin inside, you need this parameter L to be very small. If you fix the points or parameter L fixed, then the point's very far away, so that. Okay, so this was Sen's suggestion, and then sort of Scher and Singer showed that indeed this approximate Hyperkähler metric can be perturbed to an actual one. So this gives construction of DK ALF metrics in a certain limit, and sort of the actually full family of metrics can be constructed in various different ways, and was going to be relevant for this talk, in particular work by Dancer, Cherkis-Kapustin, and Cherkis and Hitchin, where actually there's an approach to these spaces via Twistor theory and Numb's equations that allows actually to produce every Hyperkähler metric, I mean the arbitrary Hyperkähler metric in this family. There's also other approaches via, say, complex Monge-Ampère methods, sort of identifying once you have clear what the asymptotics are and what the underlying complex manifold is. You can attempt solving complex Monge-Ampère equations. Okay, so higher dimensions. So I guess the starting point for our thinking with Roger was that actually the Gibbons-Hawking construction has a very neat higher dimensional generalization, which is sort of slightly more complicated, but essentially as explicit as the Gibbons-Hawking ansatz. This produces real 4n-dimensional Hyperkähler metrics with triholomorphic, so isometric action of an n-dimensional real torus that also preserves the whole Hyperkähler structure. So, and again, sort of, so first, just in a generic complex structure, and the best way to construct them both as a sort of complex symplectic manifold in a generic complex structure and the Hyperkähler metric is via holomorphic symplectic and Hyperkähler quotient construction. So on the complex symplectic side, so we fix a complex and torus written as the quotient of some complex vector space H modulo some Rankine lattice, the co-character lattice of this torus. And then instead of having sort of points in C, we now have some complex parameter lambda I, but each of them actually come with some sort of discrete data. So each of these complex there's discrete parameters which are a choice of a primitive element in this lattice and sort of multiplicity. Actually, we could have allowed that also in the four-dimensional story if we allowed orbifold singularities. And then a parameter lambda I, and then basically the discrete data gives you a way of embedding C star to the D inside T via these alpha I vectors. And so now you have an action of C star to the D on these holomorphic symplectic manifold, which is just C to the 2D times the cotangent bundle of this torus. And you can take a holomorphic symplectic quotient, and the complex parameter lambda I are just the level set of the holomorphic symplectic moment map, which you're taking the quotient. And as I said, there's a Hyperkähler grade using the Hyperkähler quotient, where now instead of having complex, so the discrete parameter remains the same, and instead of having complex parameter, you just have sort of real parameters, because now you're going to take a similar quotient, but you quotient by the real torus, the compact d-dimensional torus, and you're doing a Hyperkähler quotient, so you need triplets of numbers to define the level set of the moment map. Okay, and then to fix the asymptotics, in the four-dimensional case, we had this constant L that was telling us what's the size of the circle at infinity. Now we have we're free to choose a flat metric on these torus T, so this is some symmetric positive definite metrics on the Lie algebra of this torus, and then we get a metric that sort of, in generic directions going to infinity, looks like some sort of Riemannian submersion. The bait is flat R3n, and the fibers are flat tori with this metric determined by this matrix L. So this gives sort of explicit Hyperkähler metrics with volume growth 3n, and then as before we had just a constant, we can take that to infinity. Here we have this symmetric matrix. We can take some of its eigenvalues going to infinity, and this gives sort of intermediate volume growth from sort of 3 to the n up to maximal volume growth.
Can you recall how do you determine the real parameters, the lambda I bar from the lambda I?
No, it's not that you determine. I mean, these are extra choices, because it's not only the complex structure, but you're also choosing I mean, if you think of, you're choosing a Kähler class in a way on this complex manifold, and to find a Kähler-Ricci flat Hyperkähler metric. Okay, so the cartoon picture is something like this. So in the fourth-dimensional case, we had this C star fibration with some singular fibers over isolated point in C. Now we have this sort of the holomorphic, sort of holomorphic moment map, complex moment map for the action of this complex torus T on X. So it maps us down to the dual of the Lie algebra of this torus, so some complex vector space. And sort of the kind of generic fiber is going to be, a neighborhood of so if we take a generic point in this complex vector space and look at this inverse image, then a neighborhood of that is going to be, in X, is going to be modeled on T star of this torus. So we have this holomorphic fibration with fibers just C star to the n. And then now things are going to the fibers are going to degenerate not along isolated points, but along hyperplanes that are determined by the discrete data. So these are hyperplanes defined by this equation and taken with a certain multiplicity. And so if I'm on exactly one hyperplane, then the local picture is I have a T star T prime, where T prime is a co-rank 1 torus times one of the four-dimensional ALF examples obtained by the Gibbons-Hawking ansatz, where this multiplicity enters exactly on which case you are, and then exactly what this co-rank 1 torus inside what this co-rank 1 torus inside the larger torus T is determined by this co-character alpha I. Okay, so we have this very clean generalization. Okay, and then pursuing Sen's idea, we can imagine doing the following. So suppose that actually this torus T is as an action of a Weil group, W, so a finite reflection group. So this is acting on the torus, and it's Lie algebra. And suppose actually that this action lifts to an action on the hypertoric variety X, so that the complex moment map becomes W equivariant. So then, in this cartoon picture, we had the hyperplane in black. These are the ones that are associated to the hypertoric variety X itself. And then in Sen's picture, we have this lambda, these 2k points in R3, and then we needed to add something to the origin. Now, the origin was the fixed point of the Z2 action. So now in higher dimension, we have extra hyperplanes, which are the hyperplanes that are fixed by elements inside the Weil group, W. And then in the same way that here, transverse to a generic point of a black hyperplane, we had a Gibbons-Hawking ALF space. We could imagine to at a generic point of one of these fixed hyperplanes, we could imagine to have a transverse geometry that is the one of a Tia Hitchin or its double cover. Right, and then this gives some cartoon of some hypercalorimetric away from all the kind of multiple intersections of these hyperplanes. And I guess the question that we had was, does there exist hypercalorimetrics, smooth or mildly singular, that fill in this cartoon picture? And, well, actually it's not there are actually interesting examples of metrics that do this. So many moduli spaces in gauge theory, and particularly moduli spaces of monopoles on R3 or monopoles with singularities on R3, actually are going to have a asymptotic geometry that can be described by a cartoon like this. For example, I think this cartoon should correspond to the asymptotic geometry of a moduli space of centered charge 3 monopoles on R3 with one singularity. But anyway, so there are examples. And then another thing that we realized was that actually there are lots of conjectural examples. I mean, the sort of spaces that we're after actually have an overlap with spaces that in theoretical physics are supposed to be interesting Hyperkähler spaces, and these are these Coulomb branches of quantum gauge theory, supersymmetric quantum gauge theories in 3 dimensions with n = 4 supersymmetries. So how does this sort of, I have no idea what exactly this Coulomb branch is, but somehow through these quantum theory, so this quantum theory has a modular space of vacua, and for supersymmetry reason, this modular space of vacua is naturally expected to be some Hyperkähler space. And sort of the reason, kind of my understanding of how, so, and this sort of the quantum theory is associated with a complex reductive Lie group, G, and at least in the simplest case, a complex representation of the Langland dual group of this group G. So, and somehow this data puts us exactly in the situations that are that I started with in the following sense. So if we have a complex reductive Lie group, of course we have its maximal torus and acted upon by the Weil group. And actually there's a sort of converse of that, meaning that if you have your complex torus acted by the Weil group in the way that you want, then you can reconstruct sort of complex reductive Lie group G in a sort of unique way, except for a little complication, that is the fact that the maximal tori of SO odd and the maximal torus of SP, they're actually W equivariant isomorphic. So if you start with the data just of the maximal torus together with the Weil group, you don't know which one of the two you're going to have to associate to this. And sort of this is related to having divisible co-roots in the lattice of the maximal torus. Okay, anyway, so and then sort of you have this data of this complex representation of the Langland dual group that actually gives you this discrete data of co-characters and multiplicities just by taking the weights of these representations. Since we're taking the weights of the Langland dual, then the weights of these are exactly co-characters of the torus T. With some multiplicities, and that give you, so we know that this data, if I take all parameters, lambda I equals 0, then that gives me a Hypertoric variety that is W invariant, that is invariant under this W action in such a way that the complex moment map is W equivariant. It's actually, we say, strongly W invariant, meaning that in the complex symplectic construction, the group W doesn't just act on X, it actually acts on the whole complex symplectic construction. So it acts on these flat Hyperkähler manifold and on C star to the D in such a way that the whole construction there becomes W equivariant. Okay, so conversely, I mean, you can think if you get one of these strongly W invariant Hypertoric variety, then you almost get a complex representation. More, I mean, you're a bit more general in the sense that you actually that's the same data give you an element of the representation ring of the Langland dual group, meaning that you can also take formal sums and differences of representations. So then sort of physicists from this data have this conjectural Hyper-Kähler space associated to the group and the representation, and actually in our construction there's also this parameter L that determines the metric that's related to the gauge coupling constant, that should be related to the gauge coupling constant on the physics side, and then there's the possibility to turning on masses that corresponds to choosing this level set of the moment map to be non-zero. Okay, so this leaves, I guess, if we want, mathematicians to try to define these spaces, and in the complex holomorphic symplectic worlds, this was done by Braverman, Finkelberg, and Nakajima. They give a definition of these Coulomb branches as affine symplectic varieties. So there's some technical definition of what is a symplectic variety, and sort of checking that the construction of Braverman, Finkelberg, and Nakajima satisfies that is a recent result of Bellamy. So this construction is very algebraic. It goes through looking at a certain moduli stack and looking at some cohomology of this moduli stack, and taking spec of this cohomology to give the, so I mean, the cohomology of this moduli stack becomes the coordinate ring of this affine variety. Okay, so I guess, I mean, one can ask, I guess the main question is there any hint that these spaces carry Hyper-Kähler metrics, and is there a definition that includes this light generalization where we go from representations to elements in the coordinate ring? And also, is there a more sort of concrete, explicit geometric realization of these spaces that is a bit more geometric and less algebraic? Okay, and this is what our proposal is. So this is inspired by kind of description of decay metrics that appears in, goes back to Atiyah Hitchin, chapter 5 or 6 of the book, and sort of then to the general decay case done by Cherkes and Hitchin in early 2000. So this uses these theories of transverse Hilbert schemes, and so this is our version of the story. So we have our W invariant hypertoric variety X with this W equivariant moment map down to the dual of the Lie algebra of the torus. So, I mean, we can consider the Hilbert scheme of points on X. This is space that parameterizes zero-dimensional subschemes with length given by the cardinality of W in this case. So it's cardinality of W points in X that are allowed to come together, and when they come together, you sort of remember how they come together. Because we have a W action, then there's a sort of natural sub-variety of these, which is the one where W acts on this vector space, and the action is actually the one given by the regular representation of W. So this gives you some W-Hilbert space. So this is if you want, another way is that you the while group is acting on this Hilbert scheme, and you're looking at the fixed locus for this W action. So this is good, but it's still, in principle, it could still be irreducible. Could have multiple irreducible components. And so there's one distinguished irreducible component, which is just the closure of the locus of free W orbits. So if I have an orbit where I have exactly sort of acted upon W freely, that defines some open set in here, and I can take the closure. Okay, and that is this sort of invariant Hilbert scheme that people consider in various situations. And now, sort of, this transverse Hilbert scheme uses this holomorphic moment map. So, so we look. So here we have sort of a. So say generically we have a W orbit. So I can map it to a point in. I can attempt to map it in a sort of point in H star mod W. So in general, however, the Hilbert scheme construction is not functorial, so there's no natural map between Hilbert scheme if there was one. So there is a further open subset inside here, which is the open subset where a push-forward map is actually well defined. Okay, so this is this transverse Hilbert scheme. I mean, basically this is saying that you don't allow, say, for example, you don't allow, if I have a fixed point downstairs, then I want point upstairs that must lie on that fiber, and they're allowed to come together, sort of, they're not allowed to come together in sort of fiber directions, right? So in this sense, it's sort of transverse. Okay, so some things that, I mean, this seems complicated, but actually in this affine fx given as an affine variety, then this transverse Hilbert scheme is also affine, and as a sort of relatively concrete description in terms of the sort of equation of x, as we'll see in a moment, and sort of the regular part for sure is going to have, since our x was a holomorphic symplectic manifold, then the regular part is also again going to have a holomorphic symplectic structure for sure. So let's see some examples. So, I mean, as I said, this looks like some abstract definition, but can be made very concretely once you have a sort of concrete affine variety and you're trying to, and the action is sufficiently simple, then you can actually calculate explicitly what this transverse Hilbert scheme are. And here's a few examples where we can do it easily. I'll just give you the results. So, so for example, if we start with C times C star, so let's look first at the real four-dimensional examples. So, and I want to show how the decay surface actually arises via this transverse equivariant Hilbert scheme construction. So for example, if you start with C times C star, and then you get a Z2 action that is, so the moment map is just projection onto C, and the Z2 actions and the point ZW into minus ZW inverse. Then sort of you calculate that this transverse Z2 equivariant Hilbert scheme is just the the double cover of the Atiyah-Hitchin manifold. And more generally, if you start with Z2 invariant A2K minus 1 surface, then you get this special subfamily of dk plus 1 surfaces. So to actually get Atiyah-Hitchin and the generic surface, you need to do a bit more clever. So you need to start actually in higher dimensions, and this is really the construction of Cherkis and Hitchin. So you start in higher dimensions, so C times C star times itself, and now the Z2 action just flips the two factors, and then sort of you take a transverse Z2 equivariant Hilbert scheme, you get some real dimensional manifold, but this sort of complex symplectic manifold has a complex symplectic action of C star, so you can take a further quotient to get you down to the dimension that you want, and you check this is exactly the Atiyah-Hitchin manifold, and more generally, you can sort of start with a real dimensional hypertoric variety associated with sort of this diagram, Z2 action that is reflection along this red upper plane, and you do this Hilbert scheme construction followed by a holomorphic symplectic quotient, and here's how you get the generic decay surface. Okay, so here's another sort of high dimensional example. So you start with the cotangent bundle of the torus, and with the action of W and standard holomorphic symplectic moment map. And you do this Hilbert scheme construction, and this actually gets identified with a natural kind of affine, smooth affine variety that arises in Lie theory, which is the universal centralizer of the associated, universal regular centralizer of the associated complex relatively grouped. So this is element of a regular element in the Lie algebra together with element in the group. So there's a slice for the adjoint action on the Lie algebra that sends every, that's called the regular Zlodowy slice. So, so this regular element here is actually an element in the this Zlodowy slice, and the group G is an element that fixes it. So we're basically parameterizing all regular element in the Lie algebra together with elements that in the group that fix them via the adjoint action. Okay, so there's this natural Lie theoretic variety, and kind of this space can be realized as this transverse Hilbert scheme. Okay, and then again, as I said before, there was this ambiguity with starting with the torus, the Weil-Gaption and the group, and sort of you can get the universal centralizer of as so odd by, again, doing something in higher dimensions and then quotienting by a sister action. Okay, and then a final example, if you get just C2n is our hypertoric variety acted in a standard way by the symmetric group that permutes the coordinates, then actually this has a explicit, this transverse Hilbert scheme has an explicit description, again, in some sort of matrix, very explicit description in terms of matrices. So you get, again, an arbitrary element on this regular Zlodowy slice for GLN, and then two Lie algebra elements that commute with S, and that product is S itself. So I mean, this is just to say that if things are simple enough, then you can actually calculate. And so I guess now what you sort of, to use this really and to possibly attempt to identify with these definition of Coulomb branches given by Braverman, Finkelberg, Nakajima, there's some little bit of technical algebraic geometry that needs to be done, and since neither me nor Roger is an algebraic geometry, that we actually struggled quite a bit on this. So anyway, so what you need to prove is that actually this transverse Hilbert scheme is going to be so we know that it has this holomorphic symplectic form on the regular part, but to actually use it, you want to show that this is a normal affine variety with a sort of flat morphism down to H star mod W. And once you prove this, actually, you can use some recognition theorem in the work of Braverman, Finkelberg, and Nakajima to precisely identify their construction with this transverse Hilbert scheme, Hilbert scheme's construction. Okay, maybe let's skip.
If you are given the data, one of these
So that. Okay, so I want to, in the little time, last 5 minutes, I hope to finish on time. I want to try to give an idea. So in a way, this now, sort of going back, we had this cartoon picture, and this gives us a way to fill in this cartoon picture as in the complex symplectic sort of category. But now what really we would like to produce is some Hyper-Kähler spaces. And so of course, I mean, one sensible approach that at some point I'd like to think a bit about would be to, sort of you have your complex manifold, this cartoon picture gives you some idea of what sort of asymptotics for the matrix you want, and say, maybe when n is 2, where you don't have intersections of these hyperplanes going to infinity, then you could attempt to apply some complex Monge-Ampère machinery in this non-compact setting. But, so at some point, what seemed appealing is that maybe we could bypass any real analysis and use some, again, Twistor theory and NUMS equations to produce this matrix. And I mean, in the end, it's probably not so satisfying. It pushes somehow things somewhere else. But let me attempt to very quickly describe some of that. Okay, so we have our Hypertoric variety that is double invariant, would say in this strong sense, and then sort of we have this complex data, and then the Hyper-Kähler metric we know actually depends on extra parameters, this symmetric matrix L, and the actually triplets of kind of level sets for the moment map. Okay, so well, the construction of the Twistor construction of Hyper-Kähler metric of Hitchin, Carlede, Lindstrom, and Rocek back in the 80s says that actually we can encode Hyper-Kähler metric into complex geometric data. So what we need is, first of all, a Twistor space. So that's a 2n plus 1 dimensional complex manifold with a holomorphic projection to CP1 and fiber-wise symplectic form. Here I think I'm missing something. Is O2 valued symplectic form, and then a real structure that lifts the antipodal map on CP1 and under which the sort of the omega is invariant. Okay, so so this is it. So for example, flat space, the Twistor space of flat space is just a vector bundle that is copies over 1 to the 2D over CP1. The Twistor space of the flat metric on T star T is the total space of a certain principal torus bundle over the total space of the vector bundle O2 tensor H star on P1, and which principal torus bundle is actually this metric cell that enters in the definition of the metric, actually also enters in the definition of this Twistor space, is the cocycle that describes the principal torus bundle. And so I mean, if you have a Hypertoric variety, then you can get at least a singular model for the Twistor space by doing fiber-wise holomorphic symplectic quotient on the Twistor spaces of C to the 2 times T star T. And because of that sort of, we can also then do this Hilbert scheme, transverse equivariant Hilbert scheme construction on the fibers of the Twistor space of our W-invariant Hypertoric variety and get a candidate singular model for the Twistor space of a Hyper-Kähler metric on our transverse Hilbert scheme. So now this is easy, but actually the difficulty in this Twistor's construction is the Hypertoric metric is not really encoded in the Twistor space, but is the sort of the main result of the Twistor construction is that then one looks at the modular space of Twistor lines of the Twistor space. So these are real section of the projection to CP1. So real, so they're equivariant with respect to the real structure. And sort of their Twistor lines if the normal bundle of this section is as this specific vector bundle. So this means that the modular space actually, I mean, saying that the normal bundle is this is precisely what you need to say that locally this moduli space is actually a smooth complex manifold of the dimension of 2n-dimensional complex manifold. Okay, and then using the structure of the Twistor space, actually, on each component of these modular space of Twistor lines, you get a Hypertoric metric with a little extra difficulty that a priori this Hypertoric metric has some signature that doesn't need to necessarily be Riemannian. So really the sort of constructed the Twistor space here was easy now. To get the Hypertoric metric, you would need to find a component, construct Twistor lines, and then component Twistor lines, and then prove that the metric is positive definite. Okay, so and the so I mean, and this is where you sort of I mean, there's some sort of classical generalizations of sort of spectral curves to sort of higher rank groups where you sort of can go from these Twistor lines to sort of think of Twistor lines as cameral data of co-Higgs bundle, and then follow some work of Hitchin and Hurtubise, and I mean lots of classical things to get some sort of then reinterpret sort of co-Higgs bundle with sort of NUMS equations, actually, solutions to the NUMS equations, and the sort of, in general, the difficulty is that these sort of spectral curves then needs to satisfy some triviality condition, meaning that you need a certain principal torus bundle are going to be trivial, and that's going to depend to the Hypertoric variety, and sort of that is where we don't have there's a proposal of how to understand this condition, but it's sort of, it's not very satisfying except in concrete situation. For example, just to end on a positive note, if you, guess this was not, so if you start with the simplest Hypertoric varieties, so just this flat T star T, then actually you can make everything explicit, and you end up identifying this Transverse Hilbert scheme, which was this literary space of the universal centralizer of the group, actually is identified with the modular space of NUMS equations on the interval, with structure group, the compactly group associated with G, and sort of regular poles at the two endpoints. And actually, I mean, more. I mean, this says that this Twistor construction, the Twistor space, I mean, the metric that you get on the Twistor space is actually the L2 metric on this modular space of NUMS equations. So I guess I'll end here. Sorry.